To see such a great crowd, especially so many alumni and community visitors coming in, some both familiar and unfamiliar faces here. This is great. So it's my immense pleasure to introduce Radia Perlman, who is a very decorated and accomplished researcher, currently a fellow at Dell ENC, perhaps most famous for either inventing spanning tree protocol or writing a textbook that several people are here for autographs of. I didn't fully appreciate the book signing aspect of this, but anyway, so we're just delighted to have her here today to give some of her perspective on network protocols. So with no further ado, I will hand off the floor.
Thank you. So, the most important point I'm going to make is that not everything that you read or hear is true. And so, critical thinking, absolutely. So the network part that we're mostly going to focus on is the part of networking where you put your data into an envelope with information on the envelope, and the network figures out how to find a path through the network. So the way networking tends to be taught, which kind of drives me crazy, is, memorize these standards documents or the arcane details of some implementation that got deployed. It's as if TCP/IP arrived on tablets from the sky in its awesome perfection. And if you mention anything about ATM or ISO or something, it's only in order to make some snide comment about what idiots those people are. So my philosophy on teaching and on books is look at each conceptual problem in a network, and for instance, you need an address if you plug into a network, and I'll say, well, here's these 7 different ways I can imagine doing it. Here are the pros and cons of the different approaches. And by the way, IPv4 does this, AppleTalk did this, IPX did this. But then some people say, oh, this book is out of date. I don't need to know about AppleTalk. Or a professor will say, hey, why is there stuff in here that my students don't need to know? With the model of a student being that they have this tiny brain that if you fill them with any information that's not going to be on a recruiter's checklist, it's wasted information. But I claim if all you care about is IPv4, let's say, you'll have a much deeper understanding of it if you look at alternatives and and compare them. Much less if you actually have to design something new in the future, you ought to know what has existed before. So some professors, yes, right, so I said that. So where does all of this confusion about networks come from? Nobody actually would have designed what is out there today. So if you try to think that it makes sense, you're just going to confuse yourself. It's just, it was due to a bunch of mistakes and compromises and somebody needing to build something, so just taking pieces that already existed that they had put together. And then people coming up with buzzwords where, nobody really knows what it is, but some people think they do. But if you ask 2 different people, they'll have a different definition of the buzzword. So things are incredibly confusing. I actually like to get to the heart of what is the difference between technology A and B. So when there's 2 things that are similar, like Ethernet and InfiniBand, I want to understand what the difference is. But there isn't anyone else that seems to really do that. So there'll either be an expert on A or an expert on B. And so if I ask somebody who's an expert on A how it compares with B, they'll say A is awesome and B sucks. And I ask a B person, I get the opposite answer. So then I have to look at these 2 horrible specs. They're huge, all with their own jargon for no good reason, and try to extract what the differences are. And then if I actually figure out some things, and then I tell an A person, actually, this B thing has these features, and it works better in this case because of whatever, no problem. The A people steal the ideas, and nobody actually cares what's inside their spec. They just want credit for it. So yeah, they just want to claim that it is their spec that wins out. So then there's also facts. So I was at a company where somebody was trying to convince the executives to bet the company on this new technology that would replace Ethernet. Now, Ethernet's a lousy protocol. There's nothing good about it, but it does its job. It's like English is a lousy language, but it does its job. So why would you want to replace it? Right. And so anyway, he had all these fancy PowerPoint things with all sorts of assumptions that I don't know where he got them from. Like Ethernet can only scale to 200 nodes. Where did you get that? Whatever. And his thing actually divided packets into, information into tiny little packets. It's sort of because the only other protocol he knew about was ATM. So he decided on lots of little mini packets, which to me would say that you're getting less bandwidth than you could because everyone has its own header, which is, and then the switches have to make more switching decisions. So one of the assertions that he made was that his protocol got 4 gig of throughput and Ethernet only got 1 gig of throughput. And that drove me crazy. I was sitting there, how could this possibly be? And so in front of all the executives, I completely innocently said, were you by any chance using a 1 gig physical link when you were measuring Ethernet? So indeed, he was using a 10 gig link for his thing, and getting 4 gigs, and a 1 gig link for Ethernet and getting 1 gig. And he just casually said, yeah, that's all I could find in the lab. So now he had actually measured it, so it becomes science. Once it's put on a PowerPoint slide, nobody would ever question it again because it's been measured. So you have to be like really careful. What are you actually measuring? You're measuring one implementation of A versus one implementation of B. So don't believe something about a protocol unless you can come up with some intuition that tells you why this property ought to be true. So yeah, don't repeat things. Also, encourage naive questions, and yeah. So how to understand network protocols? As I said, the only way to understand it is to look at history. So an example of something confusing. So what exactly is Ethernet? So I'll talk about that. And how does it compare with and work with IP? Why do we have both Ethernet and IP? And people talk about layer 2 solutions versus layer 3 solutions. What's that all about? So the way, first we need to review the network layers. So something I forgot to say before, so I'm sorry. It's natural to think of standards bodies as well-educated technologists that are carefully weighing engineering trade-offs. But a much more accurate way to think of them is as drunken sports fans. So ISO was a different sports team that happened to come up with terminology for naming layers. And nobody builds things this way, and it doesn't really matter. So there's one very prominent networking book that says, ISO failed because it had too many layers. And it's like, wow, how many wrong things can you say in so few words? They're just, right. So at any rate, it's just a way of thinking about the layers. You don't have to, do all the layers or anything. So now I'm going to talk about my view of the layers, and you'll see why it's Perlman's view rather than ISO. So the bottom layer is the physical layer. It's sort of how do you signal a bit from one machine to another machine? What's the shape of the cables, that kind of stuff. Layer 2 is neighbor to neighbor. So I can signal bits because I have the physical layer doing that for me. And the next layer up, there's a way of sort of framing the packet, saying this marks the beginning of a packet, this marks the end of a packet, here's a checksum, and that's what layer 2 would do. Layer 3 actually forwards packets between links. And So like IP is sort of an example of network of layer 3. Layer 4 is sort of end-to-end stuff like TCP, where you number messages and you can retransmit things that got lost or put things back in order. And layers 5 and above are boring. So that's why it's Perlman's layer. So Ethernet packets actually are forwarded. So it was intended to be layer 2, which means it shouldn't be forwarded. So how did it wind up getting forwarded? And so I'll tell that story. So what exactly is Ethernet? So I, at that point in history, I happened to be the person to design layer 3 at Digital Equipment Corporation for DECnet. And although you think DECnet died out, the actual protocols, it doesn't matter whether you're transporting Italian or German, the same concepts work. So the things I did still are deployed. But yeah, so I was doing layer 3, and along came Ethernet. Yeah, so layer 3 was you design the packet format and what the addresses look like, and a routing algorithm that allows the routers to gossip amongst themselves and come up with forwarding tables which tell them for each packet, look at the destination address and decide which direction to forward it. So the way to compute the forwarding table, it could be done with a central node where everyone tells the central node who its neighbors are, the central node computes routes. Or you can, an ATM and InfiniBand do it that way. Or you could do it with a distributed algorithm. So a distributed algorithm, you just plug it together. There is no central node, and they gossip amongst themselves and figure out how to compute forwarding tables. So the particular routing protocol that I did, I called link state routing because each node, here it's better with a picture, each node is responsible for figuring who its neighbors are, creating a packet saying, I am Radia, I have a neighbor George at a cost of 7, Alice at a cost of 5, and that message gets forwarded to all of the other nodes. So for instance, here you have a network where A has 2 neighbors, B at a cost of 6, D at a cost of 2, and you look at A's link state packet that says, I'm A, I have a neighbor B at a cost of 6, and D at a cost of 2. So everyone will have the same database of link state packets from everybody else, and that completely describes the network. So from that, you can compute paths. So back to history, I was doing layer 3, and then suddenly popped on the scene with great fanfare was Ethernet. So I'll talk about the story of Ethernet. So it started out as CSMA-CD. That was the actual invention. Now, CSMA-CD, it was a way to share a single wire. So if you think of it, it's kind of like having a bunch of people sit in a conference room, and there's no one there to call on them, but they have to decide when to talk. I was kind of born with this protocol. I notice not everybody uses it, but CS means polite and don't speak if someone else is speaking, carrier sense, so listen first. Multiple access means be aware that you're sharing the bandwidth, so don't talk forever. And CD is listen even while you're talking in case there's a collision, and then both of you should stop. And in a conference room, yeah, there's always somebody that raises his hand and nobody ever calls on them. And then there's other people that when they're speaking and somebody else talks, they just speak louder, and so forth. But anyway, so this was the basic invention of it, was a way for a few hundred nodes to share a wire. And there's all sorts of papers about how if you try to send, too many people sending at the same time, you're going to have collisions, and you'll get even less bandwidth through kind of the more people that are trying to talk. So I looked at Ethernet and I said, whoops, this is a new type of link, and it messes up my routing protocol. So I had to modify the routing protocol in order to be efficient with this new type of link. So one example of a little thing that I did, I didn't think any of these were terribly profound. was that if you, with the link state protocol I talked about before, everyone has to report all of their links. So if you had an Ethernet with 500 nodes and everybody talks about their 499 neighbors, it gets to be a big database. I said, okay, let's pretend there's one extra node, which is the Ethernet itself, and everybody just says that they're attached to that. So instead of 500 nodes, you have 500 links and 500, one node, because there's one fictitious node, but no big deal. So Ethernet I saw as just a link in a network, but the rest of the world got all confused, and they were building their applications to work directly on Ethernet. So I wish they'd called Ethernet Etherlink rather than Ethernet. So this was very frustrating, and I would try to tell people, no, you still need layer 3. And they said, oh, Radia, you're just upset because no one needs your stuff anymore. And I said, but someone may want to talk from one Ethernet to another. And they said, our customers would never want to do that. Yeah, it's kind of easy to confuse Ethernet with a network because an Ethernet packet, you put a destination and a source on your data, and a layer 3 packet, you do the same thing, but there's this mysterious extra field known as a hop count. And the reason for that is that in a network, you can't snap your fingers and have everybody switch to a new topology if a link goes down or whatever. So in the meantime, people's forwarding tables are going to be inconsistent. And so it's a good idea to have a hop count so you get rid of packets that are, just wandering around aimlessly. So Ethernet kind of looks like layer 3. The addresses are flat, which is actually one of the geniuses of Ethernet, but it's why we couldn't hook the internet together with Ethernet instead of IP, even though Ethernet has 6-byte addresses and IPv4 has 4-byte addresses. What's wonderful about flat addresses is you can just plug in anywhere you are, and whatever you have as your hard-coded thing in your machine will work. No one else is going to conflict with it. But it isn't good for building like a large network because it's nicer to the routers if you can summarize all of the addresses within a particular circle start with the same address. But there's no hop count field, and it's not because the Ethernet inventors didn't know about hop counts. It's just it never occurred to anyone that people would be forwarding Ethernet packets. So why are we forwarding these things? So as I said, people built their applications without layer 3. So there was Ethernet and then their application. So I was in a bad mood about all this because the people who were doing that were building good applications and being real heroes at the company, making lots of money with their applications. But they would have made just as much money had they done it correctly, which was on top of layer 3. But it was hard to explain to management. So one day my manager said to me, Radia, you do this kind of distributed algorithm stuff. I would like you to invent a magic box that sits between 2 Ethernets and lets somebody on one talk to somebody on the other, which is what my entire career had been up to. But the constraint was that this had to be done in a way that didn't change the end node at all. The end node had to still work even though it thought it was working on a single Ethernet. And there were no spare fields in the Ethernet header, and there was a hard size limit. So they had a basic concept first, which was that a bridge just listens promiscuously. So this magic box will listen to every single packet on each port, store it up, and then when the ether is free, or if it's a token ring, when it gets the token, it forwards onto the other ports. So, and then it can also learn. So by looking at the source address, if this bridge here has learned that A is on this port, and then J sends a packet with destination A, it knows it doesn't need to forward it. If A sends a packet for J, it has no idea where it is, so it has to forward it onto the other ports. So this basic idea is okay as long as there's no loops. If there's multiple ways of getting someplace, the packets will just keep circulating. So one concept is to just say, just tell the customers not to put in any loops. But then you don't have any backup paths if anything breaks. And so, you know, it was ideal if the bridges could talk amongst themselves and figure out a loop-free subset of the topology. So my manager actually, when he was asking this, he asked late on a Friday, and he was going to be gone the whole next week. And this was before people read email or had cell phones or anything, so he was going to be unreachable all week. And he thought it was going to be really hard. So he said, you know, well, you know, like break all the symmetries, have no configuration necessary, and furthermore, just to make it even more challenging, make the overhead of the algorithm grow as a constant. So no matter how big the network gets, the amount of memory necessary to run this should be a constant, which is ridiculous. Linear is the best you could ever do. And it's probably going to be n squared or something. So he disappears that Friday, thinking he'd given me this impossible problem. And then that night, I realized, oh, I know just how to do it. It's trivial. And I could prove that it worked and all that. And furthermore, it scaled as a constant. And the reason it scales as a constant is to run this algorithm, all you have to do is remember the best spanning tree message you've heard on each port. So you store one spanning tree message on each port. When you receive a message, you say, is it a spanning tree message? If it is, compare it with the one you have stored. It's a trivial comparison. You throw one away, you keep the other. A spanning tree message is about 50 bytes. So if you have 7 ports, it takes 350 bytes to run the algorithm. So I was all excited. So I knew exactly how to do it. Monday and Tuesday, I wrote the spec in enough detail that the implementers got it working in just a couple months without asking me a single question. But then I had the rest of the week where I couldn't concentrate on anything else. I was too excited. I had to show off to my manager, and he was on vacation. So I spent the remainder of the week working on the poem that goes along with the algorithm. And it's the abstract of the paper in which I published it. So what the algorithm does, I'll tell you the poem in a second, is you have this physical topology where the circles are the bridges and the green lines are the Ethernets, the black lines are the ports that connect a bridge to various Ethernets. And the spanning tree decides which ports it should not be forwarding data. And so this is now a loop-free topology that reaches everybody. So anyway, I spent the remainder of the week, as I said, on the poem. So officially, I spent more time on the poem than I did on inventing the algorithm and writing the spec. So the poem is called Algorhyme, because every algorithm should have an algorhyme. So the poem is, I think that I shall never see a graph more lovely than a tree whose crucial property is loop-free connectivity, a tree which must be sure to span so packets can reach every LAN. First, the root must be selected. By ID, it is elected. Least cost paths from root are traced. In the tree, these paths are placed. A mesh is made by folks like me, then bridges find a spanning tree. So then it was really cool. The implementers wanted to build the simplest possible box. And I kind of agreed with them that this was just a quick hack, that the right thing to do was to make people fix the end nodes to put layer 3 in. You know, so what they wanted to do was to tell the customers, just don't configure it into loops, and eventually we'll update the network stack in the end nodes so that you know, you can use ordinary routers. That seemed, you know, maybe sensible, but I, of course, wanted the spanning tree to get deployed because, gee, once you do a poem and all that. But I didn't want to argue because I figured people would think I was biased, and I let management argue, and they decided the implementers should put in the spanning tree. As trivial an algorithm as it is, it certainly made the box more complicated than without it. Well, when they sold the very first bridge, it was like, yes, that was the right thing. So the story I found out after the fact was that the very first bridge they tried to sell was to the world's most sophisticated networking customer at that point. And so the sales guy went in, and the people there were bragging about all the complicated networking things they're doing. And the sales guy said, it really doesn't matter what you're doing. It's just going to work. And they said, no, we need to talk to an engineer. And he said, no, you don't. It's just going to work. So they very dubiously bought a bridge. And they had the world's simplest topology, which was 2 Ethernets and 1 bridge. And they plugged it together, and it didn't work. And they were very unhappy. And when field service came to find out what the problem was, they discovered this. You know, orange cable in the ceiling looks like orange cable. And if the world's most sophisticated customer could get this topology wrong, it was like, yes, I'm glad. And everything was working perfectly. I'm glad I thought of that case, you know, which is the spanning tree algorithm said, well, I don't seem to need to forward packets. If I ever do, I will, but, you know, whatever. So almost immediately after the concept of this spanning tree bridge happened, CSMA-CD died out. It doesn't exist anymore. So what's called the Ethernet today has nothing to do with the invention that was originally Ethernet, except, you know, on wireless links, they have some variant of it. So now the next topic is, why do we need both IP and Ethernet? So, you know, if you ask a network person, they'll say, well, IP is layer 3 and Ethernet is layer 2. And it's like, no, Ethernet is a layer 3 protocol because it gets forwarded. It may not be a very good layer 3 protocol, but it is a layer 3 protocol. So why can't we just hook everything together with IP? And I talked about why you couldn't with Ethernet because of the flat addresses. But why do we need Ethernet anymore if it's just on point-to-point links, which it is today? There's only two. Ethernet is only between 2 nodes. There's no shared links. So what do we need this extra header for? So the world has converged to having IP as layer 3. You know, before there were lots of layer 3 protocols, which also made a bridge very nice. But now everyone has IP. And, you know, it's in the network stacks. Now, as it turns out, it's because of an idiosyncrasy of IP that you still need Ethernet. And so what's wrong with IP? IP is configuration intensive. If you move a VM around, you have to change your layer 3 address. Now, this is not how layer 3 has to work. It's just how IP works. So with IP, every link has to have its own block of addresses. And if you're a router, you have to be configured with which block of addresses is on which port. And if you move from one side of a router to another, you have to change your layer 3 address. So if you have each link has a different address block, you know, for instance, this router here might say everything starting with 51 goes over here. If it starts with a 2, it goes over here. And if it isn't either of those, then I'll send it up to the internet. But layer 3 doesn't have to work that way. So there was a protocol done by a different sports team. It was ISO, and it was called CLNP, Connectionless Network Protocol. Now what that was a 20-byte address. Now that's even bigger than IPv6. But not only was it big enough, but it had a very important property that I really wish people had understood, which is that the top 14 bytes, with IP, everything on you know, one side of a router has to share the same prefix. Here, an entire cloud shares the same prefix. So the top 14 bytes works like IP, having as many levels of hierarchy as you want, but where it terminates is not a single link, but a large cloud where everyone shares the same prefix. You can jump around within that cloud and keep your layer 3 address. So if you have the same prefix as the cloud, then routing is based on the bottom 6 bytes. So this is, if you have IP plus Ethernet, IP gets you to what it thinks is a single link. But then Ethernet has to somehow make a cloud look like a single link to IP. And you need to do this awkward ARP-like protocol to find what the Ethernet address is inside that cloud. And that's, an expensive, annoying protocol. And inside there, who knows what it does, spanning tree or whatever. Whereas if you'd use CLNP, the top 14 bytes gets you to a cloud, but you don't need to do ARP because the rest of the address is right there. And then you have a genuine layer 3 protocol doing routing on the bottom 6 bytes. So again, if you have hierarchy where you have one prefix per link, there's all this configuration that is necessary of all the routers. Whereas if you have one prefix per campus, inside your campus, you don't need any configuration at all. Just plug it together. And someone has to be told what the 14-byte prefix of this data center is. But after that, no more configuration. So the single worst decision in the history of mankind, I wrote these slides before a recent election. Was that in 1992, people said, hey, the IP address is 4 bytes. That's kind of too small. Hey, why don't we replace it with CLNP? And at that point in history, all of the vendors had implemented it. And somebody spent a month showing how to run TCP on top of CLNP, which meant all of the internet applications worked. In 92, the internet was not a big thing. It was just a kind of a researchy thing. And so snapping our fingers, we would have had big addresses within a month of that decision, except, again, this sports team mentality. A few vocal people were saying, we can't let ISO think that anything they did was any good. And they didn't even really understand it because they knew that to spend any time understanding something done by, one of the morons in other committees would just be a waste of their time. So they were sure they could design something much better. And they were saying putting in CLNP would be ripping the heart out of the internet and putting in a foreign substance, whereas they could instead design something that will be just a simple upgrade from IP. That was the theory. Now, IPv6 is, because they didn't bother learning from CLNP, it's no better than IPv4 in this sense, because IPv6 still has the property that every link has its own block of addresses. And if you want to create a data center where you can move around and keep your address, you're going to have to do some other thing, like Ethernet or one of these overlay things like VXLAN or whatever. So now I'm going to talk about some obvious things that I will insult you by mentioning because it's so obvious, but everyone gets it wrong. So, version number. Most protocols have a field called version number. Now, what's that for? Is it decorative or does it have some sort of purpose? So if you look at IPv4, up there is a 4-bit field that says version number. So what is the purpose of it? So in order to start answering that, there's a philosophical question, which is what's the difference between a new version of a protocol and a new protocol? Is CLNP like a drastically different thing, whereas IPv6 is just a new version? Now, the only way that this thing makes sense is, most things have a field in it, like Ethernet has a field called ether type, and IP has a field called protocol type, and TCP, UDP has a field called port. So I think the only thing that makes sense about what's a new version and what's a different protocol is if you're going to share the same protocol type, then you are a different version of the same protocol, even if you're completely different other than the version number. Whereas if you have to use a different protocol type, you are a different protocol, even if everything else about your spec is identical. So it's basically, when you receive a package, you say, if it's a different protocol type, send it to this protocol versus that, or do you say, oh, it's this protocol, and I'll look at the version number and send it here versus there based on the version number. So if you differentiate based on the version number, you have to look at the version number field. So for instance, this is what everyone gets wrong. The IPv4 spec says, here's a field, it's called version number, put a 4 there, but they don't give you any other hint as to what to do with it. So the only way this thing of sharing the same protocol type can work is if you actually look at the version number field and say, is that me? If not, I better throw away the packet because I have no idea what's there. So it turns out that IPv6 is not a new version of IP. It's a new protocol, because they discovered that trying to send an IPv6 packet to an IPv4 node, it would just try to parse it as if it was an IPv4 thing and do who knows what. And the IPv6 spec also, by the way, just says put a 6 here. But at this point, they say, oh, well, implementers ought to know what to do. Anyway, so yeah. Now, parameters. It would be good not to have any parameters. So I actually hate technology. I can't really use a cell phone. And so I designed technology for people like me, that you just plug it together and it works. But then I had people complain to me, hey, we have customers that really want to configure things. And I said, fine, they want knobs, I'll put in knobs, but you don't have to touch the knobs. And even if you play with the knobs, no setting of it can possibly hurt you. So anyway, parameters are bad. Someone has to document them. The customer has to read the documentation. And how can you avoid having it? Well, sometimes you have a committee that can't decide how big should this field be. And they argue and they say, we'll make it a parameter and let the customer decide. And it's like, if the committee can't decide, and it really doesn't matter, don't make it a parameter. Just pick something, or automatically configure the value. So like link costs is something that get configured, and it doesn't really matter if you get them wrong, but what Novell did was, when you first start up, you send some messages to your neighbor and you figure out what the bandwidth is and round trip delay, throw it into an equation and come out with a number, and that's kind of nice. But if there are settable parameters, you have to make sure that you don't set it to an incorrect value. So that sounds reasonable. There's a range of legal values. But sometimes you have values that are legal here and legal here, but they won't interwork. So a great example of that is a concept that I was never able to explain to my otherwise bright college-age son, which is that there's no such thing as a reliable "I am dead now" message. So you have to periodically call your mother. And then, then there's an opportunity for a parameter mismatch, which is how often do you call your mother versus how long does she wait before calling the police? So when I did my protocol, which is unfortunately called got adopted by ISO and renamed ISIS. And actually, when recently Trump said that Hillary and Obama invented ISIS, people noticed that headline and forwarded it to me and said, shouldn't you get some credit? But anyway, it seemed simple enough. I didn't try to patent it or write a paper about it, but in the hello messages, when I would have routers meet their neighbors, I'd say, hi, I'm Radia. I send hello messages every 30 seconds. And my neighbor would say, okay, I will multiply that by 3 or so, and I will only assume that the link is down if I haven't heard from you for that amount of time. OSPF wanted to invent their own protocol, but basically, kind of looked at, copied a lot of the concepts from ISIS, and they noticed that field in there. But what they did with it, they didn't quite understand what it was there for. So in OSPF, I say, hi, I'm Radia. I send hellos every 30 seconds. And what the OSPF protocol does is when you receive that from your neighbor, you look at your own configured hello value. And if it's not identical, you refuse to talk, which makes the network really brittle. And why shouldn't you have different nodes? Anyway, latency. So if you care how long it takes for a packet to get through a network, you want to do the opposite of store and forward. Store and forward says you receive the whole thing, then you make a decision. Cut through says as soon as you can decide, you start forwarding the packet while you're still receiving it, and that will lower latency. So what field do you need to look at? Destination address? Okay, so let's look at the IPv4 header. Destination address is absolutely the last thing. Let's look at the IPv6 header. Again, the destination address is kind of an afterthought, the last thing in the header. So, okay, now for something completely different. So when I started my career in the early days of networking, I worried about how to plug the network together. My contributions were how to make the network really robust. The original link state routing protocol was very fragile. When I showed how to make it so that in the ARPANET, if you breathed on it, if you just injected a few bad messages, it would be down forever. And I said that's not a good way for networks to behave. You can reboot a PC, you can't reboot a network. And then later on, I did what I called Byzantine robustness, which is that the network should still work even if there's active malicious trusted switches in there. But anyway, and I did innovations to allow much larger networks and making them more manageable and usable. Things I didn't worry about because it seemed solvable is knowing who was sending you data, knowing the data hasn't been corrupted along the way. This is all like easily solvable. In theory, it sounds great. So I want to talk to my bank. So the bank gets a DNS name and gets a certificate and proves to me when I try to talk to it that it owns that name. And due to the magic of cryptography, we establish a nice secret session. This all sounds great in theory. Right, so I said that. But then I got scammed recently. So I felt I have to kind of let you know this. In reality, DNS names don't really mean anything to actual humans. So I wanted to renew my Washington State driver's license. So I knew it could be done online. I only do it once every 5 years. I don't remember the DNS name. So I do a search, renewed Washington State driver's license. And the top result looked legitimate to me. This is what it said. And I didn't notice that little thing that said add. And so I clicked on it, and everything was like I would expect. There was a nice page. I could click on replace driver's license, change of name, all these things. I clicked on it, and it asked me for my name and address and credit card. Everything was as I would expect it to be. But then when I finished, it said, you are now eligible for all of these offers. And I said, whoops, that doesn't sound right. And I looked at the site more carefully, and it didn't actually say I could get my license. It said it would give me information about how to get my license. So the service it was doing was keeping me from getting to the actual site. So I called my bank, and I said, hey, I just got scammed by this thing. And they said, well, and I said, and it didn't even tell me how much it was going to charge. So the bank said there was a pending charge of $3.99. They can't do anything about it until it posts, but once it posts, I could call them and complain about the charge. So I waited a couple days. In the meantime, they called me, the fraud department, and said, hey, are these charges fraudulent? So not only did they charge $3.99, but the next day they also charged $9.99, the day after $19.99. Who knows how much they would have eventually charged. So I explained to the bank, yeah, no, I got scammed. And so they said, okay, we'll change your credit card number and we'll deny all of these charges. But for all the states I could think of, I tried 12 states. If you search for renew Iowa driver's license or whatever, the first things in the search order are these scam sites. And, they pay Google and Microsoft to be top in the ranking. And there's no one to complain to about this. So, yeah. Okay. So, don't blame the user. So, for instance, these are scam sites. There's now more than one of them. So there'll be several of these at the top of the search order. So I happened to hit WashingtonDriversLicense.org. Looks okay. There's also a WashingtonInformation.org. And I'm sure there's North Carolina ones too. You should search. It's cute. And the site I should have gone to was www.dol.washington.gov. DOL is Department of Licensing. How am I supposed to remember that? So I hate it when people say users need more training. And I will have a slide about that in a minute. Another topic is hype. This drives me kind of crazy. People get taken in by hype. It's hard to believe when you hear stuff all around you that something could possibly be wrong. So I'm giving a talk tomorrow on blockchain, which people believe is the answer to everything. And what I plead with people is don't say, how can I use blockchain or whatever the thing is. Say, what problem am I solving and how, what is the best solution, and look at various things rather than saying, how can I apply this particular thing. Privacy is another kind of interesting thing. I don't post on social media, so I'm safe. Right? But recently I made a hotel reservation on the phone and got an email confirmation. And then I searched on Google just to see where the hotel was. And on the map, that local.google.com, it noticed the hotel and it said, your reservation is for February 7th. It's like, whoa. So, my browser, Google actually has access to everything I've ever searched for. It reads my email, and it does this always to be helpful, I'm sure. I mean, their slogan is "Don't be evil," so I'm sure they never use it for evil things. So the internet knows a lot more about me than I know about myself, and there's nothing I can really do about it. And then truth, is it the end of truth? It's possible to make fake photos and fake audios and videos that a human can't distinguish from real. And I suspect it might be so good that even if the FBI can't tell the difference. And the internet can spread it virally, and this is, a disaster for society. So user authentication. It's common to have to trade off usability versus security. And you would expect to have some sort of graph like this. The more secure it is, the less usable and whatever. But the industry has managed to hit that spot. So every site has different rules for usernames and passwords. It has to be at least N characters or no more than X. It must have special characters. It must not. There was this great thing I saw on the internet, which I don't know who to credit it to. Sorry, but your password must contain an uppercase letter, a number, a haiku, a gang sign, a hieroglyph, and the blood of a virgin. So these security questions, who comes up with these? So this is actually a set I got that was put in front of me. Father's middle name. Nope, he didn't have a middle name. Second grade teacher's name. I couldn't remember my second grade teacher's name when I was in second grade. Veterinarian's name. I don't have a pet. Favorite sports team? What's a sport? My middle name. Well, luckily I do have a middle name. It's Joy, and I typed it in, Joy, and it said, not enough letters. So, yeah, I don't want to hear we need better user training or people shouldn't click on suspicious links. You know, what's a link? What's a suspicious link? So this is a quote that I wrote. It's in my book, and once I wrote it, I said, yes, this is exactly right. And I've seen it on quote boards. So humans are incapable of securely storing high-quality cryptographic keys, and they have unacceptable speed and accuracy when performing cryptographic operations. They are also large, expensive to maintain, difficult to manage, and they pollute the environment. It is astonishing that these devices continue to be manufactured and deployed, but they are sufficiently pervasive that we must design our systems around their limitations. So yeah, so that's it. Don't blame the user. Be skeptical about what you read and hear. Oh, and know what problem you're solving. Okay, I decided I wanted to do this anecdote also. So in my book, I have these little boxes that I call real-world examples to kind of help you understand a particular concept. So about scalability, I talk about the wine glass clicking protocol, which works maybe okay for 4 people, but 7, it gets, you know, really unwieldy. And the one that's absolutely everybody's favorite is where I'm trying to illustrate that you should know what problem you're solving before you try to solve it. So this is 100% true anecdote, and it will forever cement in your mind why you should know what problem you're solving, which is that when my son was 3, he ran up to me crying, holding up his hand, saying, my hand, my hand. So I kissed it a few times. What's the matter, honey? Did you hurt it? And he said, no, I got pee on it. So, thank you.
Yeah, I can definitely relate to that story. So I think we have a few minutes for questions, and I guess I'll. What do people want to know?
Yes, in the back.
Why did CSMAC disappear? Why was it not required after SPAN?
It just turned out to be kind of cheaper not to have shared links. So yeah, just it was harder to wire the buildings together. It was better to come to a central place. And so then they said, well, it'll be a multi-port repeater. But then they decided if it was a store and forward thing, it would be sort of better. But it was interesting. One day I wandered into work and people said, Radia, nobody cares about bridges anymore. Switches are the new thing. I said, okay, what's a switch? And they explained it to me. And I said, that's a bridge. And they said, no, it's completely different. And I said, okay, I'm sorry. Could you explain it to me again? And they did. And I'd say, but that's a bridge. And they said, I said, okay, what is the difference? And they said, well, a switch has more ports, or a switch is done in hardware or something, or a switch is faster. I don't know. But basically what it was they kind of were coming at the problem from the other side, which is they started with a multi-port repeater, decided to make it store and forward, and then said, hey, we ought to run the spanning tree so that we can have switches connected to other switches, and they reinvented the same thing. So, yeah. Okay, any other questions? Maybe not.
All right. Well, I mean, yeah, do we have the ability to take remote questions?
I guess not. Yes?
Thanks for the trip down memory lane. I've been involved in the industry for a while, and one of the things I remember when we went from bridging to routing was a lot of the applications that were designed for bridging had broadcast messages, and they were easily forwarded across layer 2. And the broadcast mechanism in IP is a little convoluted due to the addressing and whatnot. So Is that also partly why, I mean, layer 2 remained important for quite a while because of the legacy applications, and it's
Right.
not really a question more, but is that, am I
Yes.
recalling that
So
correctly? Or-
the world just totally messed up the ability to do broadcast or multicast in IP. So sometimes protocols depend on it. Now, is that the right way for a, why do you need that? And so the most obvious thing is that you want to find something. Well, if you want to find something, wouldn't it be better to look it up in a directory? So maybe you might need broadcast for finding the nearest directory repository, but you shouldn't really be needing it for a lot of things. So, the fact that they kind of messed it up in IP maybe is a good thing, because you don't really want it to be easy for anyone to be able to send a broadcast on the entire internet. Though they've come up with concepts, like information-centric networking that will be doing flooding through, if anyone deployed that, and I think that's a terrible idea for them to be working on. But yeah, so that is an interesting reason why sometimes people like to do Ethernet, because they call it a broadcast domain. Yeah.
Okay, well, if there's no more questions, we can thank our speaker, and she'll be around for a minute to chat after.